All right, let's dive right into a detective story. But this isn't your typical whodunit. Forget fingerprints and crime scenes. We're talking about a mystery on a scale smaller than you can possibly imagine. A world ruled by the truly strange and wonderful laws of quantum physics.
Now this quote, it's from way back in the 14th century, but it absolutely nails the theme for today. All our knowledge is no more than rational doubt. Basically, it's saying that real knowledge comes from questioning what you think you know. And you know what? That is the perfect mindset for a detective, especially one trying to crack a case that's been cold for decades.
And our whole puzzle really comes down to this one big question. When your main suspect is a single molecule, something you can't see, you can't touch, how on earth do you get its fingerprint?
And that brings us to the crime scene, or, well, the mystery at the heart of this whole thing, the case of the blurry fingerprint. For decades, something in the world of molecular physics just felt off. Something didn't add up.
So here's the deal. For a long time, a really solid theory predicted exactly what should happen when you shoot an electron at an oxygen molecule. The theory said the molecule should vibrate, or kind of ring a bell, in a very specific, very clear way. The problem? Every single time scientists actually ran the experiment, all they got back was this blurry, indistinct signal. The theory was screaming sharp, but reality was just whispering fuzzy.
So, if you're the detective on this case, what do? You're basically hunting a ghost. Well, you're going to need a pretty special ghost hunting toolkit, one that's designed to pick up on the absolute faintest whispers from this subatomic world. And the star of that toolkit is something called electron energy loss spectroscopy. Yeah, I know, it's a mouthful. Let's just call it EELS. But don't let the name fool you. The concept is actually pretty straightforward. You just fire a beam of electrons at your target, and then you very precisely measure how much energy they lost when they hit it. Okay, so let's walk through it. Step 1. You fire a beam of electrons, and you know their exact energy going in, super precise. Step 2. Wham! An electron smacks right into a molecule. When it does that, it transfers some of its energy, and that makes the molecule vibrate, literally like you just struck a tiny bell. And then, step 3, you catch that electron on the other side and measure its energy after the crash. That difference, that little bit of lost energy, that tells you everything. It is the unique ring of that molecule. It's the fingerprint we've been looking for.
And here's a little peek at what's actually happening down at that crazy small level. You see that beam of electrons coming in? It hits this layer of molecules sitting on a surface, and then, poof, they scatter in all directions. The entire job of this incredibly complex machine is to catch those scattered electrons and very carefully measure how much energy they've given up.
Now this is what that fingerprint is supposed to look like. See those sharp peaks? Each one points to a very specific amount of lost energy, which tells you about a specific way the molecule is vibrating. It's a perfect, precise map. But, and this is the key to the whole mystery, for oxygen, this beautiful, sharp map was only what the theory predicted, not what scientists were actually seeing. So what's the secret to getting a clear signal instead of a blurry mess? Well, it all comes down to this really cool quantum thing called resonance. The incoming electron doesn't just bounce off, it gets temporarily captured by the molecule. They form this tiny, short-lived partnership. The best analogy is pushing someone on a swing, right? If you push at just the right moment, in resonance, you transfer a ton of energy efficiently. It's that resonance that makes the molecule ring out loud and clear.
Okay, but to hear that perfect ring, you need absolute silence. No background noise at all, which means you have to build the perfect soundproofed stage for these molecules. And that, my friends, requires creating some of the most extreme conditions you can even imagine.
See, the thing is, at normal room temperature, molecules are just chaos. They're zipping around, vibrating, bumping into each other like a crazy mosh pit. To have any hope of studying one properly, you have to get it to hold perfectly still. And you have to make sure nothing else can bump into it.
So how still are we talking? Well, the experiment gets cooled down to just 23 Kelvin. To put that in perspective, that's around minus 250 degrees Celsius. That is colder than the surface of Pluto. This incredible deep freeze basically just forces the molecules to stop all that jiggling.
And how isolated? The entire setup is inside what's called an ultra-high vacuum. We're talking a pressure of 10 to the minus 10 millibars. That's a vacuum so empty it makes deep space look crowded. And you need that to make absolutely sure not a single stray atom can wander in and mess up the whole measurement.
And this beautiful beast is the machine that does it all, the EELS spectrometer. It's this incredibly complex setup with electron guns, magnetic lenses, analyzers, the whole shebang. But the real hero of our story, the part that changed the game, was one specific upgrade, a brand new computer-controlled system for gathering the data. And that one little change, well, it would end up changing everything.
All right, so the stage is set. Our detective has a brand new tool in their kit. They're finally ready to crack this case wide open and find that hidden signal.
You have to understand, the old way of doing this was kind of clumsy. Imagine going to a symphony, right? And the only thing you do is make a note every time the cymbals crash. Sure, you'd capture the loudest moments, but you'd completely miss the beautiful, subtle melodies happening with the violins and the woodwinds underneath.
And that's where we find our culprit, the bad guy behind the blurry fingerprint this whole time. It was background noise. See, the oxygen molecules weren't just floating in space. They were sitting on a graphite surface. And it turns out the graphite was humming its own little tune, creating its own signal. This signal was getting all mixed up with the oxygen signal, turning the whole thing into a blurry mess, like static on an old radio.
And right here, this is the breakthrough, the aha moment. On the left, you've got the old method. It just measured the loudest part of the signal, noise and all. And what do you get? One big blurry blob. But the new computer system, it could record everything, the signal from the oxygen and the annoying hum from the graphite. So they could just digitally subtract that background noise, and when they did, wow, something incredible was revealed. That one blurry blob wasn't a blob at all. It was actually 4 distinct razor-sharp peaks, exactly what the theory had been saying for decades.
This was it, the big breakthrough. For the very first time, someone had actually seen this complex resonance pattern in an experiment. The blurry fingerprint finally snapped into crystal clear focus, confirming theories that had been waiting for proof since the 1970s.
So, I know what you might be thinking. Okay, cool. A physics puzzle got solved. But so what? Why should I care? Well, it turns out that understanding these tiny little molecular wiggles has some surprisingly huge consequences.
Look, getting the science right at this super fundamental level, it has these massive ripple effects. For starters, knowing exactly how electrons and oxygen play together helps us build way better models of Earth's atmosphere. That same knowledge is absolutely critical for things like fusion research, the quest for clean energy. It even helps astronomers figure out what's going on in those giant clouds of gas and dust between the stars.
In the end, this little detective story teaches us something really profound about how science works. The big answer wasn't some crazy new particle nobody had ever seen before. Nope. The secret was there the whole time, hiding in plain sight. The breakthrough wasn't about finding something new. It was about finding a new way to look at something old. And that really leaves you wondering, doesn't it? What other huge secrets are just sitting there, right in front of us, hidden by some kind of noise we just haven't figured out how to filter out yet? What incredible discoveries are just waiting for the next clever detective to find a new way to see?